Hello everybody, my name's Stuart Jones. I'm a software engineer at SMT. I'm also joined with Sam Webster, who is a technical trainer at SMT. The main new feature in MASTA 10 is scripting. So I'm going to talk about scripting for a bit, and after that Sam will talk about the other features that we've got in MASTA 10. Feel free to ask questions. There's two of us, so we should have a good chance of answering them. So we had a scripting webinar a few months ago. It concentrated on C#, so scripting in MASTA using C#, writing console applications, adding properties to reports and editors, and using PST and design space search, things like that. So this part of the webinar will focus on what we've been doing since then. So since that webinar, we now support Python, MATLAB and Excel. We've had lots of requests for Python, so I hope it's popular. Everything that we showed you in the scripting webinar is also possible in Python, so even if you're only interested in Python, please watch the first webinar. So I've got some examples to show you. The first example is a gear blank optimization using a Python script. It's here, you can see it on my screen. It's quite a large script, but it's not too complicated. It's standalone, it's like a console application, so MASTA doesn't need to be open. It compares the MVH response of 3 different designs, but it could be modified to compare any number of designs. I'll just show you it in MASTA. So this is a design based on the Borg-Warner gearbox using the publicly available information for it. You can see there's various accelerometers on the casing. So what we want to do is reduce the dynamic response on the accelerometers. This is the base design. So you'll see here we've replaced the wheel of the first gear set with an FE mesh. This is it in 2D view where my mouse is. So this is the baseline design. Here we have reduced the web thickness, and in the third design we've reduced the web and rim thickness. So we're going to run the 3 designs in Python and compare the dynamic response at the accelerometers to see the effect that reducing the web and rim thickness has on the acceleration. If I go to the excitation tab, you can see that the majority of the harmonic response of the dynamic response is from the first harmonic. It's this bar here. So that's what we're going to concentrate on. So this is the Python script open in Visual Studio Code. Visual Studio Code allows you to edit and debug Python scripts and C# if you want to develop scripted properties using C# or .NET. It's free, and a Python install is free as well. It supports Jupyter notebooks, which if used to programming in Python you might be familiar with. So Jupyter Notebooks allows me to run a section of code independently from the rest of the code. So we're starting from this here is a cell of code, and it will, if I click run cell, it will run the code up to the next cell. So this section of code imports MasterPy as MP. So this MasterPy is like any other Python module. You can install it using pip install MasterPy. It's hosted on PyPy. If you Google it, you'll see Connor's face, the developer that uploaded it. You need to call mp.init pointing to the install of MASTA before accessing the API. But apart from that, there's no other setup. We do all that for you. So I run this cell. It's running in the top right here. It's very quick, this cell. So I'll show you what it's done. So it's imported various modules that you get with Python, charting libraries, math libraries, all for free. Then there's some functions that are declared. So find indices is a function that finds the array indices of inputs and results from their names. There's get results array, creates an array of results for all the accelerometers that we want. And then there's a couple of methods for plotting the results. And here we have some initialization code. So we're setting the paths to the design files and the lowercase name, the excitation that we're interested in. And we're concentrating on the first gear set and the first harmonic. So then if I run the next cell, this performs gear wine analysis for the 3 designs. So this takes a while. It loops through the designs, calling into our API here, design.load, and calls perform analysis here. As it's going, it's printing out statements, so you can see how far it's got. So it's running the analysis for the first design, getting the results. So here we're setting the number of harmonics and the frequency options as well. And it's using the methods that we defined earlier at the top of the script. The advantage of using Jupyter Notebooks is that performing the analysis takes a long time, so you could leave this overnight, and then you can plot the results as many times as you want, changing the various inputs. So when this is finished, I'll run the cell to plot the results, and you'll see the response for the first accelerometer. So that's finished running the analysis. I'll plot the results, and you can see the results here. So this is top left is the baseline design. Top right is the design with the reduced web, and bottom left is the reduced web and rim. And you can see that reducing the thickness of the gear blank improves the MVH response. This isn't obvious. It wasn't obvious to me. Normally you'd think that a rigid gear blank would be the best. But making it thinner reduces the mass and increases the compliance. This affects the mesh force and transfer path. So it reduces the acceleration to the casing. The energy is caught up somewhere internally in the model. So for me, I think it's important to have a product like MASTA so that you can get this sort of result, because you can't just rely on intuition. This bottom right chart compares the 3 different designs for a single accelerometer. So this is the first accelerometer. I can change that to the 8th and run the cell again. So we haven't had to run the analysis again. We've got a different chart in the bottom right. So next, I'm going to show a very similar example, but using a scripted property in MASTA, and you'll see it's much easier to understand what's going on. I'll show the code first. It's much easier to understand what's going on because we have an object here. We haven't had to do the setup, finding the load case, finding the excitation, all that sort of thing, running the analysis. We just get a point load gear wine analysis directly. While I'm here, I'll also show you that we support IntelliSense. So if I type my object dot, you can see we can access the design and the load case. IntelliSense isn't something that you normally get that much of in Python, but it's quite important for us because there are so many properties in our API that we've done some work to support it. Yeah, so here we're getting the acceleration response, plotting it against frequency in hertz. We're plotting the linear magnitude. If you were comparing against test data, you would probably want to use the local coordinate system and get the Z component of that because that's what they measure. If I I'll also show you this MASTA property. So if you saw the first scripting webinar, you'd see the MASTA property attribute. This is the Python equivalent. So we specify the name, get acceleration response, and the description. There's a measurement and symbol as well. And we define the type, point load gear wine analysis. So in MASTA, if you go to the scripting tab, and find an accelerometer, you can see that we have the name, get acceleration response. We can see it's a Python plugin, the location of the path, and the details here. So these details are all taken automatically from the Python script. If you press calculate, it passes in the object, the point load gear wine analysis, into the Python property and runs it. So like the other scripted properties, the C# and .NET and VB.NET properties, you can create reports and add scripts to reports. So here I've created a report just using the custom report framework that adds the name and the user-defined items. So below here, so I've added the acceleration response here. And you can run this from within MASTA. As I'm clicking run, it's adding them to the chart. And you can see that we're building up the same chart that we had from the large script, from the standalone script. So here, I think this chart was probably the top right. If you close the chart and add to it again, it would start from scratch. And this works across different designs. So I can add from design 3, design 2, and here I've just added a custom table on the point load itself. So there you go. That's created the bottom right chart. The plotting capabilities in Python are quite good. You can save charts. You can also change your axis ranges. So I've changed the y-axis here, and if you look, I think it's this one, yeah. You can see that this matches the bottom right chart. Okay, for the last example, I'll show you how easy it is to write a microgeometry optimizer in Python. Python gives you lots of libraries for free that you can use, lots of scientific libraries, plotting libraries. I think it's even got FE. So on this, I'm going to use the script to minimize the TE for a gear set. So I've just opened the helical gear set. So I've added a property on the cylindrical gear set load case. This example also shows you that you can call Python from within C# or other .NET languages. This could be useful if you wanted to use the Python plotting capabilities from within an existing .NET script, or if you wanted to use the optimization routines that you get in Python. So this script this is the C# script. It's very simple. You just call run Python. It's very easy to generate this code as well. We generate this for you. You'd have to watch the first scripting webinar to see. And it just calls run Python and points to this script. So this is the script that it points to. It's again importing MasterPy and pointing towards our install of MASTA. And SciPy, NumPy, we call optimize, that just takes an object called cylindrical gear set load case, sets up the charts. So you can see that we're going to change the lead and profile, crowning and barreling relief and display the TE as well. So we override the microgeometry, and then we call minimize, which is a SciPy method. It's using Neldermead. It's got various options. I've limited the max evaluations to 30 just so it finishes quickly. We pass in the bounds for each parameter. Again, very simple, 0 to 100 microns, starting at 10. The function it's optimizing is TE. So it's optimizing this function, which returns the peak-to-peak TE after setting the microgeometry, running system deflection, and plotting a point in the chart. So again, I've created this custom report. Very simple. Got a user-defined item, minimize T with Python. You click run, and on my other monitor, it's popped up the charts. So this is using the minimize function in SciPy to optimize the TE by changing the lead and profile relief. You can imagine trying to use you could use an AI module from within Python as an optimizer as well. The last thing that I'm going to show you to do with this is debugging. It's also possible to debug your Python scripts. We provide some support for that within MasterPy. So I've got mp.start debugging. So when you call that, it hangs the script for a bit while it's waiting for you to attach. And then you can put breakpoints in. So I'll put a breakpoint in the optimization method. Click run. And start the routine. And here it's hit this breakpoint. I can step through the code. You can see in the top left, it tells me the value of various variables that we have. And this can be very useful to see what's going on. So that's that, and it's carrying on. So the last thing I'm going to show you is the documentation. We've spent quite a long time improving our documentation for scripting. It's auto generated, so we've got well over 5,000 classes now and over 18,000 properties. All those are documented here. These are all the namespaces. You can search the documentation. And you can see every property that's available within the API, and it's extensive. I'm pretty sure this product is industry leading in terms of how customizable it is. Everything that we allow you to access. We've provided some articles to go with the documentation. So you'll see we've got a MATLAB example. This is the MATLAB setup code. It's very simple. And here we've got basically the same example I just showed you, but with MATLAB. I can't run it here on this computer because we don't have a license. But I assure you it's possible. And here we've got some results that look very similar to the ones that I showed you earlier. So in terms of future work, we're working on a SolidWorks example. So now we have a .NET API. SolidWorks has a .NET API. We will be able to modify the FE from a scripted property in MASTA using the SolidWorks API. So we can do that from PST, use a scripted property in PST, parameterize the gear blank, parameterize radial holes, for example, in the gear blank, mesh it, import it into MASTA, and compare the gear wine results all automatically. We're also working on integrating a version of Python with MASTA, because setting up Python can be a bit of a pain. We'd like it just to work out of the box. And another thing we're working on is co-simulation and state. So we'd allow other software packages to replace part of our analysis loop from within MASTA. So that's it for me. I'll hand you over to Sam. If you've got any questions, let us know and we'll try and answer them at the end.
Okay, just bear with us for 30 seconds or so while we shuffle around, and we'll be right back with you. Okay, so hello, my name is Sam Webster, and I'm just going to go through some of the other changes to functionality into MASTA 10. And What I want to start off with is a couple of changes to the MVH developments. Really just encompassing different excitation types that you can implement into your analyses. And just before I actually go into the ones we've implemented here, just going to open up a version of MASTA to show you where you can import these or where you would put these into your simulation. So if I'm in my MVH mode and with a load case selected, if I go on the editor, just as a reminder, our excitation type can be selected at the top of the screen here. And what we're going to be looking at right now is the new options that are available in here, which encompasses excitation from advanced system deflection, unit force harmonic, unit harmonic force rather, unit harmonic moment, and some updates to the user specified as well. So the first thing I really want to talk about here is the unit harmonic force and unit harmonic moment. So these are FRFs, and they're basically a way of excluding the dynamic behavior of the mesh force from your simulations to make it a little bit more simple. So unit harmonic force kind of replaces excitation by transmission error in the fact that it just gives you a 1 Newton force applied in normal to the flank. And then the unit harmonic moment is a 1 Newton meter moment applied about an axis perpendicular to the plane of action at each gear mesh. A little bit more background on what these are useful for. So these two excitation types are really used to investigate the transmissibility of dynamic mesh force from the gear meshes to response locations. And this is really without considering the scale of the dynamic mesh force due to the system dynamics. So it's very useful for understanding the relative influence of the dynamic mesh force and force transmissibility on the final response. And just a small example on this. So if you consider the case that at a given input speed, the dynamic mesh force for the main mesh frequency might be relatively low. However, if we look at the final response, we might find that at that same frequency, the response is quite high. And this could well be due to the fact that there's a high transmissibility problem at that frequency from the mesh to the casing. And that's kind of what this plot on the right-hand side is trying to show us, really. So the top plot is showing us the dynamic mesh force in the orange, and then kind of a representation of the unit harmonic force, which is the straight blue line. So it's the same across the frequency range. And then at the acceleration, the bottom plot is the acceleration response, which at the same frequency, you can see there's still some peak when we're just considering the flat force. So just to jump quickly into MASTA, I've got a couple of these simulations ran just to give us a kind of a little bit of context for this. So again, I've just selected these using the harmonic excitation types up at the top here. And then if I go to my dynamic mesh force, just first of all, we can see that if I go between my excitation by TE and my excitation by unit harmonic force, we can see that we're going from a very complex dynamic mesh force plot here across the frequency range to a flat input. And then basically we would use this in exactly the same way as we do a normal MVH analysis. So we could go to our dynamic responses, for example, and see how those vary as we go across the frequency ranges. The next thing I want to show is the updates to user-specified gear mesh excitations. So what you might all be familiar with in terms of these is the orders with respect to the primary mesh order. So that was the previous behavior available, where the first harmonic is the tooth passing order and the others are harmonics of it. We have now included the ability to do orders with respect to a reference shaft, which gives you access to the following two fields, which you can see a little bit below. So the reference shaft gives you a choice of which shaft you want to reference to, and then you put in an excitation order as a rotational order of that shaft. And this is quite useful in well, one of the use cases is if you want to do some sideband analysis. So if you actually have some harmonic excitation data, maybe from a test rig or something, and you want to try and replicate that in the software, in which you're seeing some sideband activity, you would be able to put that as a user-specified excitation within the software itself, and then view that as part of the MVH results. So just a very brief demonstration of where we see this as well. So I've got two additional load cases at the bottom of the screen here. I'll go back to my editor. So I've got two user-specified excitations. The first one is using orders with respect to the primary mesh order, which was the initial or the previous functionality, which is still available. We can see all of that now is in the first harmonic. However, on my second load case, I can see now that because I've changed this to orders with respect to a reference shaft, I've chosen my reference shaft, chosen my excitation order as a rotational order of the shaft, then I've input my information much further up in the list of harmonics. So because this particular gear has 26 teeth, I've got response there at 26 and then my sidebands surrounding that. And how we would see this in the dynamic response plots is quite simple. We see them the same way as we would normal MVH results. So this is with respect to my primary mesh order, where you would just see one line at order 26. And then with respect to the reference shaft, we can see we've got this fan now, which is showing kind of the side bands of that particular thing based on our input value. Okay, so the next thing I want to talk about is excitation from advanced system deflection. So there is an option in those excitation types called advanced system deflection current load case setup, which uses the current load case advanced system deflection setup as an excitation for input to MVH. Now, a bit of a disclaimer about this one, just so you're nice and careful when you're using it. You want to ensure that your advanced system deflection study covers a full period in whatever it is you're analyzing, so that you are sure that the TE trace is suitable for a Fourier transform with a rectangular window. So without that consideration, you might get some kind of artificial features in there which could stop any kind of accurate results would appear due to the non-periodic signal. So an example of this is if you're looking at TE variation over the entire rotation of a shaft, just make sure that you have exactly the right system setup which shows you the full period of that shaft rotation. So we've got a very simple example to demonstrate on this. A bit of background on the example itself, first of all. So it's a very simple spur gear pair. And all that it has applied to it is sinusoidal pitch errors, which are on the pinion only. So there's no pitch errors on the wheel, only on the pinion. And we have a very low torque load case. So the advanced system deflection simulation is running one full rotation of the pinion shaft. And if we look at the TE plot in the advanced system deflection mode, this is what we're kind of pulling out here. So you can see a full period of pitch errors based on that information we've got input into the model. Okay, so if I jump back into MASTA, I'm going to change to that appropriate model. Okay, so what I'm going to look at here is the excitations. So because we've used advanced system deflection here, if I just jump back to my editor, just to show you where I got this setup from, again, back in the harmonic excitation types, we're looking for advanced system deflection current load case setup. Under the excitation, we can see it's brought through that transmission error plot that we were just seeing in the presentation. And then as a result, we've got harmonic amplitudes here, which are occurring at our tooth passing order. So basically what we can do here is we can actually use MASTA itself to get kind of sideband information from manufacturing errors or radial asymmetry in the model, which we're pulling in from advanced system deflection. Okay, then once we've actually set up that particular section, we can just analyze the results exactly the same as we did previously using the MVH mode. So this is the associated dynamic response plot from this, where we're seeing all these excitations. I can also view that as an order map as well. Okay, so I want to move on away from MVH now and talk about a few more of the modeling developments that are available in MASTA 10. So the first thing I want to talk about is gear teeth meshing. So this is the ability within MASTA now to create FE meshes of the gear teeth in the actual FE mode. And this can be added both to imported full mesh FE. So let's say you had a gear blank which has some radial holes cut out into it, so you actually need to import the FE. You can put gear teeth from MASTA on top of there. Or if you've generated the shaft FE within MASTA itself. So just a side note on how MASTA handles the connection between those two things. So it automatically handles any mismatch in the mesh between the teeth and the body using multi-point constraints. It's worth noting as well that mesh teeth don't alter the connections of condensation nodes governing the tooth meshes. So they remain connected to the root diameter. So I'll just sort of demonstrate this within MASTA again. So I have two very basic gear blanks set up here. The first one here has been created from the actual shaft which I'm replacing, which has been done inside MASTA itself. And the second is an imported gear blank because we've got these basic radial asymmetry in the gear blank. With these two loaded in, I can go to my meshing options tab within the FE mode. And I just have this new option down at the bottom of the screen here, which is showing me the gear meshing options. And it's basically just allowing me to select whether or not I have teeth in my model. Once I've selected, I click mesh volume. It recalculates the mesh with the gear teeth included. And as I say, the join between the two different meshes is handled by multi-point constraints. Okay, and then the next one down is, as I say, that imported FE, so it's slightly different on here. Because we've already imported the FE, we again go to our meshing options. There's slightly different layout of settings here because we've not got as much control over our mesh in this one. I can click that I want to mesh the teeth and then just say update the mesh. I have full control as well over the density of the mesh on the teeth, but it is worth mentioning that at this stage, this teeth meshing option is really just for the mass of the teeth for using MVH calculations. It is a step towards being able to do LTCA in this particular one without having to build that separate advanced LTCA model elsewhere in the software, but that's still a little bit further down the line. Okay, so a bit of a note on the imported FE section of this, where we put the gear teeth on top of the imported FE. The gear blank should be cut off well below the root diameter of the gear. We actually need to be able to calculate some of this intermediary section here using the same meshing procedure as we do for the gear teeth. But it's worth bearing in mind that if you are bringing in a gear blank which doesn't require FE gear teeth, you still want to bring the blank up to the tooth root diameter, or that's our recommendation. Okay, so I want to talk briefly as well about the flexible spline couplings. So in MASTA 9, I believe, we introduced the ability to put in some flexible splines, which kind of represented by this image in the foreground here shows that we have two condensation nodes for each of the spline teeth, just controlling the side fit here. That's since been updated slightly to this image in the background here, so we've now got a major fit diameter option as well, which includes a radial clearance property. So we can also add some ability to contact on the top of the teeth as well. So what this option does is it adds another node to the tip of the teeth, and these work in the same way as all the other condensation nodes in MASTA, that they have an adjustable search region, and you can modify which particular nodes on the FE those are connected to. Okay, so a brief example of this. This is a model we have already set up, which shows the side fit or the two-node system. In order to change this, I'm just going to go to my design mode and find the corresponding spline component. And on the default editor for that side spline component, about halfway down, we have this type of fit. So I'm going to change that from a side fit to a major diameter fit. And then it gives me a radial clearance option down here. So if there is some radial clearance between the spline teeth at those particular points, I can put the value in here. And then with this major fit diameter selected, if I go back to my FE, I can see that it's now got a third node on the end of each of those teeth. And it does have an associated search region for those as well that I can use to locate nodes. Got to make sure that we do this for both the ring gear and for the ring gear component itself and for the corresponding connection, which in this case is on the casing. Okay, so a couple of small upgrades on the bearings. So we have put in the ability for asymmetric ball bearings. So you can specify the shoulder heights independently for ball bearings, which I'll show you in a second. And we also have the ability for cross-bearing conical profiles. So previously we would just have a conical profile spanning one row, even for double row bearings, which is kind of represented by this image on the top here. So you would have the same conical profile specified on each of the rows. Now you have the ability to make that conical profile span both of those rows, and it will end up with something along the bottom here. So it's kind of a continuous profile along the entire two rows. So to bring both of those into the software, to specify those options, I'm just going to select any old bearing for the time being. Okay, so I'll start off with a radial ball bearing, go to my race details, and you'll see I have full control over my shoulder properties down here. So I'm going to adjust the height of those, for example. Now I've got independent control over the left and right options. For the roller profiles, if you bear with me for 1 second. I'll go into edit my bearing design, go to profiles, and you'll see on the inner and outer race where I have the active profile type, I do have the ability to specify a conical profile. And with that selected, I've now got the option to create a profile that covers 2 rows of elements. So I select this, put in whatever modification I want to see. It's a little bigger so we can see it. And then the 2 plots on the left-hand side here are showing you how that's been distributed across the two rows. So we have the top one here, which is starting from just above 0 and extending to just above 40 microns. And then the second row is starting just above 50 due to that gap in the middle of the 2 rows, and extended to just below 100. You also see a small visualization on the 2D plot as well of how that's continuing. Okay, so there's been some slight update in the way that we save FE files externally. So previously we just had one big SMTFE file for each piece of FE. That's now been split into 2. So we've got the SMTFEM files, which is containing mesh information, and the SMT FEV files, which is containing expansion vectors and is much, much larger. So this has basically been put in to speed up the user experiences, as large vector files can remain unloaded until they're really required. And users can specify which configuration of these that they want to either export from the model, embed into the model, or if they even just want to open the mesh rather than loading in all of the vectors. And this is controlled in the same location that the previous export of SMTFE files was done. So I go to my imported FE, just select any one of my models here. And then underneath the import and export tab, I've now got two different sections under here, mesh file and vector file. And they basically allow me to embed those into the model, to store them in the model, load or unload them. Okay, a small word on the electric machine data import. So this previously was specified on a load case, if I remember correctly, but it's now been moved slightly. So it makes a bit more sense where it is now. It's been moved onto an actual imported FE model, and the data is actually now stored within the FE model itself. We've also added the ability to do force visualization, showing radial, tangential, and axial forces in a sort of polar plot format. So when you have an FE model created and one of your power loads is set to be an electric motor, you will get this option when you're specifying your imported FE, which shows electric machine data. So this one already has some imported. So you can add a data set to a particular load case. Data sets occur over on the right-hand side. And then if I edit one of these, we get the same format of data entry that we did in MASTA 9, just in a different location. And we now have this force visualization option as well. This gives you a bit of a different representation of how the loads are being distributed. It's worth mentioning on the electric machine front as well that we have two new example MASTA models, one which is demonstrating a skewed rotor and one which is demonstrating an axial flux motor. Sorry, I can't get my words out. Those are both in the example menu within MASTA. And the very final thing I want to mention to you is the ability to save parametric study results. So results generated within parametric study tool can be saved and reloaded. And this is only possible when the data is being logged. So the results are saved to an external file or embedded within the master file will automatically be loaded when opening a design. And then very briefly, just to show you where this is done, I'll go to my parametric study tool, and then on my editor with a load case selected, it's just the options down at the bottom here. So I can, once I've run my results through, I'd have the ability to save out the external file for later use, or I could load results from an external file as well. It's worth noting that if you do make any changes to the model and therefore the hash code of the model changes, MASTA will recognize this and give you a warning when you're trying to load in some results. Okay, so in terms of the actual functionality, that's about it. There are a couple of questions that have come in very briefly. One is asking, for the sideband calculation, do we need to have advanced system deflection? I believe the answer to that one would be a yes, because it's behavior that you do need advanced system deflection to see. And then will the webinar be available after the, or video be available after the webinar? Yes, that's also true. So the webinar will be updated and uploaded to the MASTA main website as well. So one final thing I want to speak about is future webinars and future events that we have upcoming within SMT. So if you go on our website, www.smartmt.com, we have a couple of sections up here covering webinars and events. So we have a lot of upcoming webinars which are now fully available to register for. So any of those links there will allow you to register for any particular one you're interested in. And we also have upcoming events as well. Specifically, we have some training workshops in Europe coming up very, very soon. And we have some user forums as well in the US, in Europe, and in China. So please go on the website, take a look at those pages and see if you're interested. And we'd love to see some of those as well. So there's a small flood of questions coming in now as well, asking when MASTA 10 will be launched.
Yeah, it looks like we've got a few people asking that question. MASTA 10 is feature complete, which means that we've added all the features into the software. We're just doing the testing and bug fixing required before we release it. The answer is as soon as possible. But everybody, including my boss, is quite keen to get this released. We hope it's the order of a couple of weeks rather than a couple of months.
Okay, so I think that's about it from us. We will stay on the line for a few minutes if there's any more questions come in. But apart from that, thank you very much for your attention, and we hope to see you at some future webinars or future events. Thank you very much.